Hey,
Hey,
Luca.
Thomas. Hey. Yeah, Friday again.
Yeah,
Good. Yeah,
very
it
good.
looks like I'm either right before Thunder sessions, during Thunder session, or right after, and then it's already right before. You know, things happen. A lot of things happened this week as well. But what happened last week in the last episode was that we took the Liger kernels, which are kernels developed by a group in LinkedIn, over kind of overfit on how the model is laid out in Hugging Face transformers, and then we applied it to a model that we developed, but independently, of course, of this effort, which is LeadGPT, one of our flagship repositories, open source projects for pre-training, fine-tuning, and serving LLMs. And then we said, okay, let's use Thunder to get the optimizations from Liger into LeadGPT without having to change LeadGPT. And we did that. Well, not all of them. For three of them were RMS norm, rope cache, which is, remember, the positional encoding piece that we briefly reviewed. And then what was the third? Sweet glue.
Swiglu, and then there's the fused cross
Oh,
entropy
yeah.
with
Exactly.
Liger, right?
And the fuse cross entropy, which is one of the most important ones, of course, because it allows us not to materialize a lot of data that we should otherwise materialize when we evaluate the loss. And yeah, that was great. It actually produced the same numerical results, which is amazing. But then we looked at time. And so when you go through this exercise and say, okay, let's do it, let's take optimized kernels, apply it to my models, uh, you cannot expect that this will just magically be faster, or you can hope for it. If you have your own tradition, in Italy we take salt and throw it behind your back. You see all sort of things people do when they watch their favorite soccer team playing, but usually that doesn't result in a lot of good stuff. And so what you need to do is you need to measure. You need to measure to see the before and after. And in case you're slower, just like is in our case, what's the process? Do you change kernels? You dump Liger for something else? No, that's not a good idea. Um, you actually go in and try to start probing what's going on. And so this is what this episode and probably the next will be about. We open the lid and see what's in it, and we'll follow Thomas in this process to understand what's going on. And I think there's a lot of neat things that will be useful regardless of LeadGPT, Liger, or even Thunder. So yeah, let's get to it.
Yeah. So uh, before we properly start, I want to let me share my screen. Before we properly start, I want to call out new contributor to Thunder, which is always like one of the exciting things. And so here, Nachicat 18 and Ultra Artois 3, they submitted implementation for a zip look-aside. So remember, we re-implemented all of Python more or less in Python in the interpreter. And so for the built-in zip function and data type, we want to be able to track what's going in, what's coming out. And this tracking requires that we re-implement the zip function. And so the two took that, and it was merged today. So that's awesome. Congrats if
Amazing.
you're watching.
Yeah.
And obviously, we're glad to have you. Okay,
Yeah. And that's also, by the way, this is not a trivial piece of the stack, right? So writing a look-asides is not too complicated, but it's not even, not the easiest thing ever. So congrats. Yeah, for sure.
Yeah, I mean, many look-asides of this nature, they are straightforward in the sense that you basically uh, uh, have a Python function that does the thing, and then the look-aside needs to call the Python function.
Yep.
Whereas in the standard C Python, it's implemented in C for performance reasons, and
Yep.
we for non-performance reasons we do the other thing. Okay, the other thing that got merged into Thunder uh, uh, is the Liger kernel notebook that we showed last time. So it's here in the Thunder repository. If you want to try it out, you can. And we can do this, right? We can just run that, restart, and run all cells.
Yep.
Okay, so we can go back up. We had this. We defined our executor. We imported here the Liger kernel, the functions, and then we implemented them one by one and checked them. And then there's the Liger example, and for the benefit of the CI, this is disabled in the official source code repository. But we also ran this, and now we ran into the first problem here. And also for the benefit of speed, I greatly reduced the number of samples. And now we're running into a problem. Oh, the checkpoints path does not exist. This is true. That is because the checkpoint is in the main directory. So I can just, oops, sorry about that. I can just change to the proper directory, right, at the top.
Yep.
Let me do this here very, very manually. Os dot change dir, and we want to change to the main directory, which we need to, I think we need to spell it out, right? In order for it to work.
Yeah, I'm not sure. It's Team Space Studios, this studio.
Right.
Yeah, exactly.
And this is, of course, from the studio magic. I could re-download the thing or copy the notebook
No, it's
main
fine.
directory, but so this is how it goes. And now we can preload, load the pre-downloaded weights, and now Thunder needs to compile. And this was one of the things that was a problem. So currently, and of course, one of our colleagues, Jay, is working on fixing this. Currently, Thunder will only process fixed shapes, which is a thing that like all new deep learning compilers do. They specialize on the shapes. Um, and this means that if we have different shapes in every call to it, it will retrace the entire model, and this will like take quite a while. And we see this here. The epoch, it should just do 7 batches of 4. But it seems to take forever, and we're not seeing our GPU being used, which is not so nice. This is, by the way, one of the awesome things I like about the studios. Of course, it's a bit biased because I work for Lightning, but I used to like open a second notebook that had a little script to call NVIDIA SMI all the time and then report the number. But now I don't need to do that anymore. But we will come back to the GPU utilization soon. So here you see that it has processed the first batch in about 42 seconds, and it wants to take 4 more minutes to do the entire thing. and it would be nicer if it just compiled fewer times. And so
Yeah,
the thing
just
we do,
to just to spell it out, like where do the different shapes come from, right?
yeah, so they come from the different sequence lengths in the data set. And so the data loader will pad all the sequences to a given number, but it's not obvious from the start what that number would be. Uh,
Yep.
if we scroll through the source code, we can see that it has here the data collator for completion only LM, which is like a function that aggregates the batch. And it says here patch to multiples of 16, and we will broadly bump it
Hmm.
to 512, and then we will be a lot faster. So
Yeah,
here,
because basically now we get a prompt of like, or an input of like, 10 and then 60 and then 100 and then 200 tokens, and they will always be padded 512, no matter what. And so the shape that will go in will always have 512 in the sequence direction, and the others are fixed. So that's the only one that is
yeah,
changing for us.
we might also see something like 1024 or so,
Of course, yes.
but it will be a handful and not like a different one on every
Yeah.
iteration. So let's restart the kernel and run everything.
So the solution for this, the right solution for these, is to introduce symbolic shapes so that the compiler can reason about something being a shape or a dimension in the shape, but without a fixed number,
Yeah,
right?
on one hand, that is the case. On the other hand, there might be reasons for various optimizations that only apply
Yeah,
to fixed shapes. It might be reasonable to bucket the shapes better, like
yeah,
we do here, even if the Thunder compiler could handle it. So, for
yeah,
example, if you use
100%.
CUDA graphs or something as an optimization, which we will get to maybe not today, but later on in a later episode, um, it will be something that benefits from having granular buckets of
Yeah.
shapes that all map to the same thing. So
Perfect.
now it compiles this hopefully only once, and then we can see what's up. But while it's doing its thing, we might as well also be busy. And so afterwards, we want to look at the performance of the model. And in order to do this, we need to get a batch of inputs. And so let's do this. We just grab this from the data module, so from the train data loader. I don't have the top completion here because it's still running the other thing. So we need to grab a batch from that, and the train data loader is a function that is an iterable. And so we need to get the iterator from it, and then to get the batch from it, we just call next. So this will be our test batch. And we saw now here that it basically compiled the entire thing once because it only took 43 seconds, which was the
Yeah.
time to get the first iteration last time. And then the padding made all other 6 things go very fast. And now it's like cleaning up things, maybe compiling the evaluation once. But so here's the batch. The other thing we need is, and the batch we want to move to CUDA in a bit. So batch will be k, and it's all values. So we can just say, well, let's wait for it. the other thing we want to do, we want to move the model back to CUDA. So PyTorch Lightning by default, I think, moves it back to the CPU after training. And so we move it back to the device. Okay, so let's do these two, and let's look at what batch is here. So just to be clear, here we solve the first performance thing by batching, right?
Yeah.
Or by properly doing this. And now we have the one batch here. And so in order to make this a bit easier for us, let's grab these, put these into separate variables. So here are the input IDs, and we move it to CUDA. And then we have the attention mask. I'll just call it mask. And that needs to be moved to CUDA. And finally, we have the labels, and there we had this thing that only the last set of labels is the interesting one. And so we took the liberty of just picking those. And
yeah, because we're predicting the next token, right? So to us, let's say ground truth is the next token with respect to the input sequence, what came immediately after. And so we're taking that label there.
Well, so really this is a text classification thing. And so these are the labels for the classification. Okay, so we see that model.model is our Thunder module. And we can run it with the input IDs, the mask, and I required the last two to be keyword args, and I think I named this targets. Maybe inputs. Yeah. No input. Oh, input IDs. Maybe I should standardize on input IDs if that's what the name is. And here it's missing labels. I didn't rename it to targets after all. Okay, silly me. Now we see it's running, it's recompiling. I don't know why it's recompiling here, because it should have it in the cache. Maybe the moving to CUDA isn't something that it likes very well. Oh yeah, it will not like that. Oh no, I don't actually know why it doesn't like it, but maybe we will figure it out later.
Exactly. That's the point. Let's see.
Okay. So we get from calling the model, we get our loss, and it has a backboard function. And so if we do it a second time, it will be fast, and we can go and time it. And the first thing I always do is to just time it with the time it built in the Jupyter notebook. But then I need to not forget to use torch CUDA synchronize in order to be sure that it finishes everything on the GPU before moving to the next thing. So this takes about 40 milliseconds, and we can compare it to the original model, which is still here by accessing this underscore model. And of course, it takes the same inputs as the Thunder model. And we see that it's a bit faster. So quite a bit faster, actually. And so we need to figure out what's going on here. And so Luca promised a lot of measurement today, and so
well, just a few. Then we'll have more next week. It's an investigation problem at this point. but
Okay.
it's one that you'll need to go through if you implement your own kernels. There's no escape from measurement.
Yeah. So my slogan always is, if you don't measure, it's not optimization. Um, and
Yeah.
I guess that's just how it is. So in
Yep.
order to get a more detailed look at what's going on, we can. I should say one thing first, though, too. If I promised to do this earlier, but if we look at the GPU utilization, if we run the full thing, the GPU utilization will look a bit like. Oh no, it doesn't like it because I didn't use the GPU enough, probably.
You may have a snag on the metrics. What's going
Yeah,
on?
too bad.
Maybe you can reload the page and see. Yeah, this is interesting. We need to send it to people.
Yeah, obviously
Yeah, here.
yeah.
Yeah,
Uh,
we're a reload away from it. I think something going on with the
right,
WebSockets.
and it could be the connectivity on my end, right? Um, so one thing that happens is if you have like the GPU only utilized every now and then, like now, there's a huge time where it's not used, and this is because we have been chatting in between. But if this happens in your training loop, you also have this problem to fix first, because obviously, if you optimize the GPU kernels, you're only going to shrink the time that has the good GPU utilization, and you can save on that. But if that is like a small fraction of the total time spent, you will optimize a tiny thing and you can't gain much, because if you only have 10% GPU utilization, the best you can get by like making the thing that happens during GPU utilization faster is 10%, and the other 90% you need to do something differently. So usually we would go and look at the data loading first and maybe cache the ready to consume tensors. But now let's look deeper into the model instead and look why the Thunder one is slower than the non-Thunderized one. And to get a bit more inside, the next stop after a quick timeout is usually for me, it's the PyTorch profiler. There's also tools to profile in Thunder, which we will introduce later. But for now, let's go with the Torch profiler. So in Torch profiler, and I think we saw this in the first or second episode also. You just have this context manager Torch profiler profile, and you give it a name, and then you just run whatever workload you want to analyze in this section. And then this goes fast, but then if you take the profiler, you can take the key averages, and in this there will be a, you can show these, but this is a bit like dense to look at. So it has a formatting function, so you can say, I want a table, and I want this table to be sorted. So sort by, I think, self device time total. And if I do this, it's a string. I need to print it. And now we see, except that it's
a bit narrow, yeah.
funnily, and now it's hard to read. But what can you do? You have to choose one of the.
It's like my multifocal glasses, you know.
Yeah.
It's almost good, almost always, but it's never really good.
Yeah. but so in order to get a view of what's going on, let's compare this to the original model, the one that was not compiled. And what we see is, yeah, it's a lot of kernels. What we see is that here, if we look at the CUDA time total, we see that in the first line already we have like a 5 millisecond discrepancy, and this is in the matmults. And in addition to this, if you compare it carefully, you see that here's a Cutlass kernel that's probably an attention module. And this is here again. And those are the next two here. While we have, in addition to the MM that is slow, we also have an add MM that
Yeah.
like 6 milliseconds self CUDA in addition. And then there also is 6 milliseconds the GEM K1 kernel. And so
Yeah.
we will need to figure out like where these come from and why they're taking that much more time in the in the in the execution than the matmults in the original model.
Yeah, it's interesting also because they come from A10, and A10 is the library from PyTorch Eager that powers a lot of Eager, or almost all of it. And so, yep.
So speculation is a bit, you have to be a bit careful about speculating here. But one thing could be that we've changed the strides of the kernels inadvertently or something like that, and then these need to do extra work. But at this point, we don't know, and we need to take a more detailed look and also compare it in more detail in order to figure out. So what we'll do next time probably is take apart the model and profile it bit by bit. So we will run, for example, the self-attention layer separately, and so to see like what is really the part. If we look at the overall model again, we see here we have the GPT for the fine-tuning, which has a linear layer as the head. For some reason, it's at the top, even though it's the last thing that's being called. It should be at the bottom, but it's the order of registration. But so we have a linear layer. Then we have the transformer, which contains of the embedding, which is at the beginning. And then there is a number of blocks. And these blocks are always of the form: you have a norm, you have the self-attention, you have another norm, or you don't have the norm here, it's for other modules. And then you have the llama MLP and another norm here. So somewhere here we're getting slower, and it might be either in the final bits, or it might be in the MLP, or it might be in the attention part, or in the norm. And which it is, we will have to figure out.
Yeah, it's interesting, right? Because like a very naive interpretation of what we did is, oh, Thunder made it slower, or Liger has slower kernels compared to PyTorch.
Yeah,
You can't say any of this, right? You need to, go and measure and understand that now there's something that makes like us do more operations, and it's probably something in between something that is adding that.
I mean, one thing we could do here is, and this plays weird tricks with the notebook format. is we could skip all the custom operators
Mm-hmm.
and go right to the. Did I also skip the monkey patching? Yes, I did. So and we could go right to the example now, and of course this will recompile. And so what I did now is I'm running the model. Yeah, and it doesn't work. We will need to. Oh, it's the GPT for fine tuning last token. So I moved things around a bit, and now you can't run them independently anymore. But what we can do here is grab the model and the definition and just run that separately. And so this will give us a version of Thunder without the Liger modules. And
Mm-hmm.
I would predict here, I didn't try it in advance, so
Let's
my
see.
prediction would be that this is at least as slow as the thing with the Liger kernels. Oh no, it's, yeah, I didn't define the transforms, so I need to take those out too.
Yeah. Yeah, while you're doing the work is like, I will just reiterate what the idea that you had. Since we're changing the model a little bit in order to accommodate for the Liger kernels because they are laid out in a certain way. And so we made in the transform, we made slight modifications to the model in order to, do the bridge between the way things are in LGPT land and the way things are in Liger land. And so right now we imagine it's not the Liger kernels being slow. And so in order to test that, we just don't add the Liger kernels, but we keep with the modifications that we're doing in the transform in. And so we kind of validate the idea that is these modifications that are introducing extra operations. And so
well, so what I'm doing now is I took away the transforms too. And what
mm-hmm.
it does now is it runs the same module with the standard transformations and executors that Thunder comes with. And it could be, so one thing of Thunder is that it
I see.
decomposes operations into things that might be more compiler friendly. But sometimes we hit something, oh no, it's not working yet. Yeah, now it's, why does it
I
not?
see. So look at it, and I'll replay what you just said. So Thunder comes with a few sets of for example, decompositions and things that we do behind the scenes to make life easier or easier if you want to downstream executors. And like, for example, NBFuser, which is a fusion executor, likes to feed itself with primitives because it can reason through primitives a lot better than it can through high-level operations, where they're too high level for NBFuser to fuse and meaningfully do its work. So you need to break it down for them for NBFuser. Now it's possible that in doing so, we in that process, we do this introduction. So even before the transforms that we introduced for Liger, we want to see if the extra operation pop up even without any of that. So
Right.
that's what we're trying to figure out.
And we should be good to compile now. And the thing is that we need 1 or 2 bits to make this particular model that we use with the custom masks for the fine tuning. We need to accommodate these, and now it will just run through the tracking epochs, and then we can see, like, will this be 40 milliseconds? Will this be even more, 50? or will this go down a bit, and this will inform like the first thing we will look at next time. But so let's see what coming up here, because
Nice.
yeah.
I love this. Like this has become a whole project, which is great. And we are not doing a ton of work outside of this episode. Of course, there's some preparation, but as you can see, we're figuring things out as we go, which I think it's very informative for whoever's watching. And not just for the Schadenfreude part of it, but also for the thinking process of it.
Yeah, but if you want slow thinking, always watch me on video.
Oh no.
Okay, so here it
that's good. That's good.
Epochs, and now it needs to do something. There was a delay always here. But so let's start the next few things, and we are all like eagerly waiting for it.
Exactly.
Which is one of the things that kind of makes these things like a bit tedious. And one of the tricks I've done in the notebook, and that might be if you have something like that, we saw that there's a number of blocks, and if you need something that runs quicker, of course, one of the things is you can reduce the number of blocks here with the n layers argument. And if you're just interested in does it run or does it not run, this will give you a speed advantage. And so this is what we usually do for testing, and I did this above for the unit tests, that we see like the replacement properly, and so this makes it considerably faster if you do development. But obviously, if you at the end, if you want to say, well, we're running Llama 1 billion, you need to run all the layers.
Yeah. And if you're doing 70 billion, yes, it's even more challenging.
Yeah, so if we don't play any tricks, we're actually a bit faster than without compilation. So there's something going on that costs us really dearly when we add the Triton kernels to the mix. And so the next time we will do the ablation of finding like what's really going on.
Yeah, nice. Okay, so we're good from the, you started saying, oh, maybe it's us, maybe it's like what we do normally. It's not that, fortunately, but it would be cool anyway, it's a journey. So now we need to see what this things in between that we used to adopt one thing for the other, what it's bringing in terms of additional operations. And yes, and then maybe we can also next time maybe look at some traces and see like profiling traces are very interesting to look at. But even without getting into profiling traces, because this is the other message, right? Oh, I need to profile. Oh, I need the full trace, and I get lost in that trace. No. You just start from time it, percent time it, very high level. Then next step is compute how long we're spending on operations and sort them from biggest offender to the smallest offender, and then get your way. There's no magic, right? It's just a discovery process that you need to go through.
Yeah. On the other hand, I mean, if you do that right, you can like achieve the performance of highly optimized models without changing actually the models, just by layering in the optimizations. And so we will do.
Exactly. Okay. So thanks a lot, Thomas.
Thanks, Luca.
And thank you, everyone, and see you next Friday.
Yeah. See you. Have a good
Bye-bye.
weekend.
Thanks. You too.